project looks at the stress within a thermoelectric module due to a thermal gradient. It was created by Barrent and Trevor Ruckle. On the right you can see a picture of an actual thermoelectric couple we've made, and you can imagine hot gas from the exhaust system flowing through the center and a cooling jacket placed on the outside to cool the module. On the left, the cross-section view shows that every couple has an N and P leg, and that for our analysis we will be modeling the cross-section of one scoterdite leg. The thermoelectric material consists of 4 different layers. Proceeding from the inside to the outside, it consists of titanium, scoterdite, titanium, and copper. Due to symmetry, we can model only a quarter of the part. As you can see here, at the symmetric interfaces, it is free to move in one direction and constrained in the other. A portion of the outer ring, seen in green, was also fixed to make the analysis a little more complex. For the thermal boundary conditions, a heat flux was placed on the inner constraint, highlighted in red, along with a convection to the environment constraint placed on a portion of the outer ring, highlighted in pink. The values of these boundary conditions were derived from test data taken of the actual module. We created our own program to generate our mesh. Within the program we can subdivide each of the 4 material layers into any amount, along with dividing it radially into any even number. The figure shown is divided into 20 radial divisions, along with dividing the 4 material layers into 3, 15, 3, and 5 subdivisions. We first need to find the temperatures at each node. This is done exactly as in homework 6. We first need to find the stiffness matrix contributions along with the force matrix contributions of each of the boundaries. Here we compare the temperature distribution of 2 plots with different mesh sizes. The upper left has 20 radial divisions, where the bottom right has 60 radial divisions. You can notice that the temperatures gradually increase from the bottom right to the top left due to the insulated boundary condition. The results of both mesh sizes are similar and only show a maximum difference of less than 2 degrees between elements within the same area of the mesh. To find the stresses within each element, we first need to find the displacements of each node. To do this, we need to calculate the force matrix from the thermal preload. The force matrix for each element is calculated using 2x2 Gauss integration of B prime times D times alpha delta T times the determinant of J, where alpha delta T is the thermal expansion coefficient times the temperature at the integration point minus the initial temperature of the body. Once the displacements within the element are found, we can then compute the strain from multiplying B times U, where B is evaluated at S and T equals 0. After that, we can then calculate the stress within the element by multiplying D times the strain. From there, we then can compute the principal stresses, and then finally we compute the von Mises stresses from the principal stresses. Here we compare the stress distribution between 2 meshes, one with 20 radial divisions and one with 60 radial divisions. As you can see, the results of the mesh refinement show little change through the model except at the node on the outer radius, where the boundary condition transitions from the displacement being fixed to being free. As a second check beyond mesh refinement, a unigraphics model was created and a finite element simulation was run to verify our program. The model was a 3D model that is of unit thickness and thin compared to its length and width. The mesh size was set to be 1/4 millimeter and used 3D triangles. The same constraints and boundary conditions were applied as in our own code. The temperature results between the unigraphics simulation and our program are almost identical and correlate very well. The stress distribution results between the unigraphics simulation and our model trend the same and have similar values. Some of the differences in the results may be from using a 3D model compared to a 2D model, mesh size, and mesh shape, even though a lot of the values are almost identical.